Imagine you are tasked with solving a murder mystery. All the clues are laid out: fingerprints, alibis, a weapon. But the challenge is connecting them logically to identify the culprit. Now, what if you had a brilliant assistant who could reason step by step, ensuring no clue is overlooked and every conclusion makes perfect sense? This is the essence of logical reasoning, a skill vital not just for solving mysteries, but for breakthroughs in law, medicine, and AI safety. Yet, even our most advanced AI models struggle with this. Today, I'll introduce you a groundbreaking framework, Selection-Inference, that transforms how AI tackles complex reasoning tasks, making it both accurate and interpretable. Let's start with some background. Large language models have demonstrated remarkable capabilities in few-shot generalization tasks. They're able to perform language tasks that they weren't specifically trained on and require few or zero examples, but they consistently struggle with multi-step logical reasoning. To address these limitations, the authors introduced the selection-inference framework. This modular system alternates between selecting relevant facts and performing inference, which creates a chain of logical reasoning steps that are both interpretable and causal. These qualities not only improve accuracy, but also enhance trustworthiness of LLMs in critical decision-making tasks. To understand the foundation of the selection-inference framework, let's briefly explore neurosymbolic models and their role in logical reasoning. Neurosymbolic models combine the strength of neural networks and symbolic AI. Neural networks excel at learning from large datasets, while symbolic AI is valued for its logical reasoning and interpretability. Neurosymbolic models bring these two paradigms together, using specialized modules for tasks like comparing facts or applying logical rules. These models have several advantages. Their modularity allows them to generalize to harder problems, requiring long chains of reasoning. Additionally, they provide interpretable reasoning traces, which offers a step-by-step view of how conclusions are reached. However, these benefits come with challenges. The specialized modules often rely on handcrafted designs, making them difficult to optimize and adapt to new domains. Their scalability, especially for real-world problems, is limited. The SI framework draws inspiration from these models. It embraces their modularity and interpretability, but replaces handcrafted modules with pre-trained language models. This approach retains the interpretability of neurosymbolic systems while adding the flexibility and generalization capabilities of modern LLMs. Now let's look at the problem and how the selection-inference framework addresses it. Despite their capabilities, LLMs often fail when tasked with complex multi-step reasoning. For example, solving logical problems that require chaining together several reasoning steps remains a significant challenge. Traditional approaches like chain of thought prompting introduce explicit reasoning but do not ensure that the reasoning steps are causal or interpretable. The selection-inference framework tackles this by breaking reasoning into two modular steps: selection, which identifies a subset of relevant facts from the provided context, and inference, that uses these selected facts to deduce a new intermediate fact. This iterative process creates a reasoning chain where each step builds logically on the previous ones. The modularity of the framework not only improves accuracy, but also provides a transparent reasoning trace, which is critical for applications requiring trustworthiness. Speaking of chain of thought, let's quickly talk about it. Chain of thought prompting is a method designed to guide large language models to produce explicit reasoning traces. It extends the input prompt by including examples that break down problems into intermediate reasoning steps before reaching the final answer. For instance, instead of just answering who is the tallest based on the given context, COT encourages the model to state intermediate facts like Alice is taller than Bob and Bob is taller than Charles before concluding that Alice is the tallest. This approach offers two key advantages. First, it improves performance on complex reasoning tasks by encouraging the model to think out loud. Second, it enhances interpretability by showing how the model arrived at its answer. However, COT has some more notable limitations. The reasoning traces it generates are not always causal. Steps may not logically depend on one another. Additionally, the traces can sometimes contain errors, even when the final answer is correct, which raises concerns about reliability. This is a comparison between the vanilla LM and chain of thought prompting. We can see that on the left figure, figure A, the model is provided with context and a question. For example, what is Emily afraid of? And is expected to directly propose the answer, mice. While the model arrives at the answer, the process remains a black box. There is no explicit reasoning trace to show how the model linked Emily is a wolf to the fact that wolves are afraid of mice. This makes it challenging to validate or trust the model's reasoning. Additionally, without an explanation, errors in multi-step reasoning tasks are harder to debug. For the figure on the right, this is the chain of thought prompting approach. This method introduces intermediate reasoning steps into the model's output. For instance, when asked what is Emily afraid of, the model explicitly states wolves are afraid of mice and Emily is a wolf. Therefore, the answer is mice. This trace makes the reasoning process transparent and easier to understand. By breaking problems into smaller logical steps, chain of thought improves performance on more complex reasoning tasks. Now we'll talk about the selection-inference method. The selection-inference framework operates as an iterative process. It alternates between two key components: the selection module, which identifies the subset of facts most relevant to answering the question, and the inference module, which deduces new facts from the selected subset and updates the context. This modular structure ensures that each reasoning step is interpretable and causally linked to the next. Unlike black box approaches, where reasoning is implicit, or even the chain of thought framework, the SI framework provides a clear reasoning trace. To implement this, the authors used pre-trained language models, relying on prompt engineering to guide their performance. For instance, in the selection phase, the model scores the relevance of each fact and selects the most likely ones. In the inference phase, it deduces a new fact to add to the context. This iterative process continues until the final answer is reached, making it highly adaptable to multi-step reasoning tasks. Next, we'll see some prompts for selection and inference modules. This is the selection prompt. We can see that this is the format of the example. We first provide the context and a question, and we repeat the example for n times. And finally, we provide the context and the question we would like it to solve. And similarly for the inference prompt, we provide the example in this form, and the facts in the prompt are the ones selected by the selection framework, and now we want it to reach a conclusion. And we also repeat the example n times, and we provide a new problem for it to solve, which is the problem of interest. And now we'll talk about the selection-inference algorithm in more detail. First, we'll talk about the inputs, the n-shot prompts for selection and inference. These are just templates that guide the language model to perform the respective tasks with a few examples. And the initial context, C0, this includes facts and rules relevant to the reasoning task. And the question Q is the problem that we want the model to solve. And the language model LM is the model performing the reasoning. And the halting function is a function that determines when the reasoning process should stop. In other words, when the model has reached a final conclusion. And for the core part of the algorithm is the iterative process. We first start from step 0 and continue until the halting function is satisfied. So we first start with the selection step, and at each step the selection module is invoked. The module takes the selection prompt, the current context, the question Q, and as inputs, and its job is to identify the most relevant facts from the context that are needed to proceed with the reasoning. And for the inference step, it uses the inference prompt and the selected facts to generate a new inferred fact or conclusion. And a newly inferred fact is then fed back into the context, which expands it for the next reasoning step. This ensures that the reasoning chain builds progressively. Finally, we update the counter T, which is just moving to the next step in the reasoning process. The loop continues until the halting function is satisfied. This function is a very important component as it determines when the framework has enough information to confidently answer the question. Once the reasoning is complete, the final selected fact is returned as the answer. And this diagram basically illustrates the algorithm that I just described. You first have the selection step, which has just a bunch of examples of the selection process, and the question we're asking is we don't want it to give an answer. We just wanted to select the most relevant facts. So in the selection module, the final answer provided is just a fact or a bunch of facts. And the examples are repeated k times, and then we feed the answer to the inference module. And in the inference module, we also repeat the example for k times. And the example is just some facts and a conclusion. And in the inference step, we actually wanted to give a conclusion. And now let's talk about the performance of a selection inference. The authors evaluated the selection inference framework on 10 logical reasoning tasks from datasets like BABI and Proofwriter. These tasks varied in complexity, requiring anywhere from single-step reasoning to multi-step inference. The results are pretty impressive. The 7 billion parameter SI framework achieved a 58.75% generative accuracy, significantly outperforming the same 7 billion parameter model used in vanilla or chain of thought approaches. Notably, the SI framework even surpassed a much larger 280 billion parameter baseline in both generative and multi-choice settings, showing its efficiency and robustness. And this is the diagram that shows the accuracy increases as we move from a vanilla model to chain of thought to selection inference. And we can see that the selection inference outperforms the other methods by a lot. And then finally, we'll talk about some of the limitations and the future work of selection inference. Well, first, it relies on well-posed, contextually complete datasets, which may not always be practical in real-world applications. The framework currently requires a predefined number of reasoning steps, lacking a robust halting mechanism. Tasks requiring extensive planning or dealing with ambiguous information remain challenging. And also, its performance is heavily dependent on prompt engineering, which can be resource intensive. Here are some future directions of selection inference. First, developing dynamic context extraction capabilities could allow the system to retrieve necessary information independently. An improved halting mechanism would enable the model to decide when to stop reasoning, which enhances efficiency and accuracy. Refining the selection module to evaluate multiple reasoning traces could further strengthen interpretability. Finally, fine-tuning the framework on step-specific reasoning datasets could significantly boost its overall accuracy and reliability. Before we end the presentation, I have a little demo to show. So this demo is based on the BABI dataset, and in this dataset are just a bunch of logical reasoning tasks. In particular, I've chosen a task that basically has a bunch of events at different time steps, and for each event is either a character has possession of something or the character enters into some location, and by the end of the story you need to the model needs to answer which object is in which room. So first I'll show the selection prompt. And this is an example I provided for the selection prompt. You first start with the story. You have characters doing stuff at different time steps. And you ask the question, where is the apple? And for the selection inference, for the selection module, you don't provide the answer, but the reasoning that the model needs to reach the final conclusion. In this case, we need two facts, which is that Daniel got the apple and Daniel went into the bedroom. So that's the only two facts we need to know in order to reach the final conclusion. And in the paper, I believe the authors used 5-shot prompting. So I included 4 more examples in the prompt. And then finally, we append the story and the question we want the model to answer. So it is able to give the correct reasons, which is John picked up the football and John journeyed to the bathroom. Next, we have the inference step. For the inference prompt, similarly, I have generated 5 examples, which is that we select 2 facts. We use the facts from the inference from the selection module, which are 2 facts, and we use these facts to reach a conclusion. So this is the question we want the model to answer. So this is up to the inference prompt. We wanted to complete the sentence, the conclusion after therefore, and is able to give the right conclusion. The football is in the bathroom. And yeah, that concludes my presentation. Thank you for listening.